Have you ever wondered what the C code running your car's engine has in common with the C code that keeps a satellite in orbit? It's not actually the language that's different, it's the world it lives in. Today, we're diving deep, we're going bare metal to really demystify embedded C. Now, I know it can seem a little intimidating at first, but stick with me, and you're going to discover this whole new world of absolute control and power.
So let's just get the biggest misconception out of the way right from the start. Is embedded C some kind of totally different language from the C you already know and love?
The answer is a big, resounding no. Nope, not at all. The syntax, the keywords like if, for, while, it's all the same C. The real difference isn't the language, it's the playground. You're writing C, sure, but this time you're on a tightrope, and there is no safety net below you.
And this slide right here, it just nails the difference. On your desktop, you're living in what we call a hosted environment. Think of the operating system as your personal butler. It manages memory for you, it handles files, it even kicks off your main function. But in the embedded freestanding world, well, you're on your own. There is no OS. You are the one who has to tell your code where memory is using a linker script. Your code only runs because the hardware reset vector literally points to your startup code. And that huge standard library? Yep, forget about it. In this world, you are the operating system.
So to really get this, we're going to go on a little journey, peeling back the layers one by one. First, we'll really nail down that distinction between regular C and embedded C. Then, we'll explore that freestanding world, learn how to talk directly to the hardware, get good at bit manipulation, and unlock the absolute superpower of pointers. I promise, by the end of this, you're going to have a whole new embedded mindset. Let's do this.
All right, first stop, the freestanding world. In this realm, you're not just a programmer anymore, you're the system architect. You don't ask the OS for memory or resources, you build the entire universe for your code, right from scratch.
And your main architectural tool is something called the linker script. Think of it as the treasure map for your microcontroller's memory. It tells the compiler and linker exactly where to put every single function, every variable, whether it's going into permanent flash or volatile RAM. And let me tell you, if you get this map wrong, your device won't even turn on.
Okay, take a look at this memory block. This is from a real linker script. It looks simple, but it is incredibly powerful. We are literally telling the linker, hey, over here, at this address, we've got 256 kilobytes of read-only executable flash memory. And over at this address, we've got 32 kilobytes of read-write RAM. This is the absolute bedrock of your firmware. Everything else gets built on top of this foundation.
So we've got our memory map. How do we actually use it to interact with the real world? To blink an LED or read a sensor. The answer is this really clever technique called memory mapped I/O. Memory mapped I/O is just brilliant. The hardware designers literally map the control knobs for all the peripherals, your GPIO pins, your timers, to specific memory addresses, which means we can control incredibly complex hardware just by reading and writing to a memory address with a plain old C pointer. No special libraries, no OS calls, just pure, direct hardware access. Now here's a super common scenario. You need to wait for a piece of hardware to tell you it's ready. The obvious way to do this is to create a pointer to that hardware status register address and just loop until the value isn't 0 anymore. Simple, right? I mean, what could possibly go wrong? And here it is. This is the million-dollar question that trips up pretty much every single new embedded developer. The code looks totally correct. It probably even works perfectly fine when you run it in your debugger with optimizations turned off. So why does it suddenly catastrophically fail the second you build your code for release with optimizations turned on? The problem is your compiler is just too smart for its own good, and the solution is one little keyword, volatile. Without it, the compiler looks at your while loop and thinks, hey, nothing in the code changes this value, so to be efficient, I'll just read it once and then loop forever. Volatile is your way of shouting at the compiler, hey, don't you dare optimize this read. The hardware can change this value behind your back at any moment. It's the shield that protects you. And here's the fix. See, just by adding volatile to the pointer declaration, we force the compiler to perform a fresh read from that memory address on every single loop. This guarantees you're always seeing the real, live value from the hardware. The key takeaway here is simple. Any pointer that points to a hardware register must be declared volatile, no exceptions. So now we can reliably talk to our hardware registers. But what about writing to them? See, a lot of the time, a single 32-bit register controls a whole bunch of different settings. To handle that, we need to master what's called bit banging, manipulating individual bits with surgical precision. So you've got two ways to do this. On one hand, you've got bit fields. And yeah, they look really clean, almost like accessing members of a struct. But trust me, they are a trap.
The C standard doesn't actually guarantee how they're laid out in memory, which makes them super non-portable. Change your compiler and your code might just break. The professional standard, the way the pros do it, is with shifting and masking. It looks a little more complex, I know, but it is 100% portable and gives you total, unambiguous control. In production firmware, this is the only way to go.
And that brings us to the most fundamental safety procedure for messing with bits, the read, modify, write operation. It's a simple three-step dance. First, you read the register's current state into a temporary variable. Second, you modify only the specific bits you care about in that temporary variable. And finally, you write that entire modified value back to the hardware register. This process ensures you never accidentally clobber other important settings in that same register.
Okay, we've seen how pointers can access data and hardware registers, but what if they could point to actual code? In the embedded world, function pointers are not just some obscure C feature. They are a superpower that lets you build dynamic, flexible, and really robust firmware.
The concept is actually really simple when you break it down. A function pointer is just a variable sitting in RAM that holds the memory address of a function that's living over in Flash. That's it. It's a bridge, letting you dynamically connect your runtime data space to your compiled code space.
So where do we use this superpower? Oh, you know, just about everywhere that matters. Function pointers are the absolute backbone of modern firmware. We use them for interrupt vector tables, for driver callbacks, for customizing an RTOS, for state machines. They're what allow our code to be reactive and dynamic. They let you decide at runtime which piece of code gets executed next. Now, with this great power comes a pretty serious warning. You have to respect the underlying hardware. For example, on ARM Cortex-M chips, the least significant bit of a function's address isn't part of the address at all. It's a special flag that tells the CPU it's running in thumb instruction mode. Now, the compiler handles all this for you automatically, but if you try to manually mess with a function pointer's value, you could easily corrupt this bit and instantly crash your entire system. The lesson is clear. Let the compiler manage function pointers for you.
Wow, okay, we have gone all the way from the high-level idea of an execution environment down to the nitty-gritty of flipping individual bits in a hardware register. So now let's just pull it all together and define what it really means to have an embedded mindset.
To think like an embedded C developer really just means internalizing these core ideas. It means you understand that you are the architect of memory, using linker scripts to draw the map. You speak the hardware's native language through memory-mapped I/O. You know the compiler is a powerful tool, but one that needs to be guided, so you shield your hardware access with volatile. You control every single bit with precision using bit masking. And you wield pointers to control the very flow of execution, building dynamic systems with function pointers.
And really, that's what embedded C is all about. It's not a new language, it's a new mindset. It's a mindset of total control and total responsibility. You have the map, that's your device's datasheet, and you have the compass. That's the power of C. The only question left is, what are you going to build?
If you like this one, the YouTube algorithm says you're going to love my other videos, so go check them out.